Well, before I start talking about the problem itself, I'll make some advertisement. And here is where our university is based in São Paulo. Is one of the largest cities in the world. And São Paulo always gives me mixed feelings because it's a really nice city where you can actually do whatever you want any time of the day. You just bump into really, really cool stuff, but there are 20 million people doing the same thing as you, and it's super crowded, a lot of traffic. And here is the university, right in the middle of that craziness of São Paulo, but just a few kilometers away, we have many beaches and mountains. So you can enjoy that for a weekend if you like the beautiful beaches or the peace of the mountains. And we also have Guarulhos Airport, one of the largest in Latin America. Maybe if you're traveling to Brazil or Argentina, you have to stop at Guarulhos. And if you want to stay for a few days, you can visit us at the University of São Paulo. Our campus, despite São Paulo may be a bit crazy, our campus is really nice. A lot of trees, is really peaceful where we work. And we are one of the major universities in Latin America. We have around 9,000 students, counting undergrad and grad students. And we are responsible for 18% of Brazilian scientific research. So it's a big university with a lot of opportunities there, especially for the young ones that are here. And now we have a São Paulo State Quantum Initiative with a lot of funding, positions available. You can apply for that anytime. So if you're looking for other opportunities, Brazil has a strong community in quantum information, and we have position available there. Let me know. Okay, so this is our group. We have now 2 postdocs, Naim, which is the main responsible for the work that I'm showing you. And Danilo also worked with this, Luis. Luis and Naim were former students of Gabriel Landi, and master's and undergrad students. Okay, so now let's go to the problem itself. Today I want to talk about this paper that is in arXiv, and in which we want to relate contextuality, which is some form of non-classicality, as I'll try to explain in a moment, in a thermodynamical situation where we are trying to connect anomalous heat flow with this kind of non-classicality. And in this problem, we are looking at situations in which heat flows from the colder to the warmer systems. That's why it's called anomalous. And this happens because we are using correlations between these systems. We are consuming these correlations in order to perform this task of anomalous heat flow. But what we want is to understand what we can do with quantum systems that perhaps we cannot do with classical systems. That's the main question. And there are examples of heat flow reversals. They are caused by classical correlations. So the presence of anomalous heat flow alone cannot guarantee that we are looking at a quantum phenomena. It might happen because of classical correlations. And what we want to do is what we would like to do is answer the question, what kind of heat flow we can get with classical correlations, and what kind of heat flow we can get with quantum correlations. This slide basically summarizes my research as a whole, because in different problems, I'm always trying to understand what is classical from what is quantum. And in this specific work I want to talk about today, we want to differentiate between classical and quantum heat flow. Okay, so as Vida said, I have a more mathematical background, so I need a formal definition of what I call classical. So this word appears a lot when we're talking about quantum stuff, and it can mean a lot of things depending on what you're talking about. So what I want to do now, the first step, is to give a very precise definition of what is classical, okay? And there are many debatable points on everything I'm going to say today, including this. I can talk about these problems later, but for now, I would take this definition and work with it. Maybe we have to change it, but that's a problem for the future. Okay, my working notion of classicality is what we call generalized contextuality. That started with the work of Rob Speckens in 2005. And it's one notion of classicality that is used a lot. And this is also debatable. I'm talking a little bit about these problems later. But what I wanted to, the message I need you to take from this slide is that the use of the word contextuality is contextual. Different groups have different definitions. They are related, but they are not equivalent. So every time you hear contextuality, you have to know which kind of contextuality they're talking about. But the goal is always to find a mathematical formal definition of what I call classical, okay? Okay, today our notion will be that. So to start the definitions or to start talking about this contextuality, I need a very abstract way of dealing with physical systems. So it's the most abstract way you can possibly describe what is happening in a lab, which we call operational theories. So in an operational theory, we just list a set of specifications of what you do in the lab and some way of computing the probabilities that will come out of this lab procedure. So what do we need here? We need a list of preparations that will tell you how the state of the system is coming out. I do not necessarily need to say that is a density matrix of a photon. I don't care about that specifically. I just have a list of preparations. A list of transformations of some, it can be a time evolution, or it can be just a one-step map that you're doing with your system, some transformation, and a list of measurements with the corresponding outcomes that we will call effects. But for now, there's no mathematical structure here. It's just a list. And in the end, I need a rule to compute the probability. So I want to know the probability of getting outcome B, given that I'm measuring M after preparation P and transformation T. Okay, so it's very abstract. I'm not talking about specific states or systems, just probabilities. And now I spend most of my life trying to see if these probabilities can be recovered from some classical probability model or quantum and seeing the differences between those. Okay, another important thing here in these operational theories is what we call equivalences, because different recipes, different preparations can give you same probabilities for every measurement. So we say that two preparations are equivalent if they give you exactly the same probabilities for every measurement and every transformation. And I'll have the corresponding definitions for transformations. So we say that two transformations are equivalent if they give the same probabilities for every measurement and every preparation. And two effects are equivalent if they give the same probabilities to every preparation and every transformation, okay? Sometimes you can just work with preparation equivalences, so this can be, this can change depending on the problem you want to attack. Okay, so one example, quantum theory saw as a operational theory. So the preparations are density operators. So you know that a density operator, the same density operator can describe many different preparation procedures, even in different physical systems. The transformations are CPTP maps. Maybe you can relax this a bit, but for now it works for us. We're mainly going to use unitaries, so that will be enough. And effects are POVM elements. You can also relax this a bit, but this is also enough for us today. And probabilities are computed using the Born rule. So these probabilities here, we can also assume that they come from an underlying mathematical structure, but maybe I'm not interested in that, so I forget about the whole mathematical structure that is behind and look just as the probability. Okay, so now we go to the possible classical explanation for those things. So this is where the notion of classicality comes. It's what we call ontological models. That's the name that Specken used. And this is very much related to another name. I prefer this, but maybe you have heard before, hidden variables. So that's the same, exactly the same idea. So the idea is to explain your operational theory by this underlying hidden variable or ontological model. And I want to make assumptions that make it look like classical probability theory, okay? So first, we start with a set of states that we call ontic state, our hidden variables. And to every system, we associate this set of ontic states. And we assume that these ontic states, that's the entire idea behind introducing them, they specify all the physical properties of your system. So it's the idea that you know the ontic state lambda, you know everything. If you like a bit of mathematics, that is a measurable space. We won't need to go into the details, but you can make it more formal in terms of probability theory or measure theory. And the preparations, they sample this ontic state from a probability distribution. And that's why maybe you cannot specify all properties of your system. It's because you don't know the underlying ontic state. You just have a probability of having certain ontic states with measure given by this MIP, which is called the epistemic state of your system. And this gives you a map that takes each probability, each preparation P to this probability distribution over the set of ontic states. And they basically satisfy this property. They are all positive and sum up to 1. If you're here, I'm assuming that the ontic state is finite. It's not necessary. So if it's not, you change this sum for an integral. This might make your mathematical calculations a bit hard because then you're working in an infinite space, but things work. Okay, now the transformations, they determine how likely it is to move from one ontic state lambda to another lambda prime during the process of the transformation. And this is just a stochastic map defined in this measurable space. And this is a map, it's a matrix, a linear map that takes probability distributions defined in lambda to probability distributions defined in lambda. And this thing here gives you the probability of ending in state lambda prime after the transformation t, given that you started in state lambda. Now for the measurements, each measurement is presumed to have its outcome sampled at random depending on the ontic state. Here is something that some people disagree, because if you assuming that this thing here gives you the entire knowledge of your system, sometimes people require that this measurement has definite outcomes. So it's not sample at random, but it's lambda gives you with certainty the outcome of measurement M. For finite sample spaces, it's equivalent. From this, you can construct one that is deterministic. For continuous variables, it is not equivalent. So sometimes people forget about this sampling at random and just use deterministic things. So it's something that is debatable here. So assuming that you can, I'm assuming that I'm allowing for the outcome of the measurement to be sampled at random, then each effect is connected to what we call a response function that gives me the probability of outcome B, given that my state is lambda, okay? So this gives the probability of having outcome B for measurement M, given that the state is lambda. Okay, now I constructed the respective representatives for preparations, transformations, and measurements. But I want to do this in order to reproduce the predictions of my operational theory. So now these things, they have to match with the probabilities that I had in the operational theory. So the probabilities that I had before have to be given by this rule. Probability of having lambda times probability of starting in lambda, ending up in lambda prime after transformation, and probability of having outcome B, given that I am in state lambda prime, sum it over all possibilities, okay? Okay, so now I want to study if I can reproduce the statistics of a given operational theory with some ontological model. A completely mathematical structure, I have no physical reason to prefer one or another. I'm just seeing if it exists. But without further restrictions, every operational theory can be described by an ontological model. It can be a completely crazy ontological model. It can allow a lot of things that are not physical. That's why we now make some restrictions to recover the notion of classicality. That's what we want to define. And for what we call non-contextual ontological models are the ones that satisfy these conditions. If I have two preparations that are equivalent, they have to be taken by the ontological model in the same probability distributions over the set of ontic states. The same goes for transformations. If two transformations are equivalent, they have to be taken to the same stochastic map. And if two effects are equivalent, they have to be taken to the same response functions, okay? And the word non-contextual here is because these different places in which the preparation appears are different contexts, and I want this to be non-contextual. It does not depend on the context. Okay, now with this restriction, you have a lot of things that cannot be reproduced by this kind of ontological model, okay? So for example, you have situations, measurements, preparations in quantum systems that cannot be described by non-contextual ontological models. Okay, so today, our working definition of classicality will be the existence of a non-contextual ontological model capable of reproducing the observed data. As I told you before, this is debatable. In foundations, there are people that think that this is too strong. There are people that think that this is too weak. And if you are interested in this debate, you can see this paper that has been out on arXiv like this week. And where we discuss this is in a joint work with one of my PhD students and John Hans from the UK. And maybe this article will not be that interesting for you, but there are many references there that might be, okay? So where these things are discussed. I'm not going to this debate here, that's not my goal today, but I just wanted to make clear that this is not a consensus in the community. And which makes room for more research, okay? So this notion of classicality is used in many situations, and I wanted to show you two applications. There are more, but I just chose two that I think they are interested. I'll just mention them, and then I'll go to the application I want to talk today, which is the thermodynamic study of quantum transfer. So one that I think is really nice is the state discrimination. So you have two preparations, and you want to make a measurement to decide which preparation you have. Is preparation 1 or preparation 2? And within quantum physics, you can compute which is the best measurement that you can do. This will give you the minimal error state discrimination protocol. And in this paper, which is the work of one of the papers in the PhD of David Schmidt, he is now in Poland, I guess. He's back at Perimeter, nice. And they derived limits on this minimal error rate state discrimination if your experiment is described by a non-contextual ontological model. And they show that situations in quantum theory violate these bounds, showing that for quantum systems, you might have an advantage over these classical models. And another interesting application of this is this work that I like very much. And this is mainly the work of Roberto Baldijão, was a postdoc at our group. Rafael Wagner was a master's student. And my group, he did his PhD with Ernesto Galvão in Braga. Now he's in Pisa in Italy. Cristiano Duarte, also a very old collaborator, and Marcelo is my PhD supervisor, so it's a family thing. And in this paper, we studied quantum Darwinism was the main subject of Roberto's PhD thesis. And in quantum Darwinism, what you want to do is you have a central system interacting with several other systems, environments. And you want to see how information about the central system is spread to the environments. And you want to see if these environments agree on the information they are seeing about the central system. And this agreeing on this information is what they call objectivity. And in some sense, you want to say that this objectivity is related to classicality. And what we wanted to do is to see if this classicality could be related with non-contextuality. And what we answered for this, we were looking at a very special, at a model for Darwinism. It's the Brandão, Piani, and Horotesky model. And we see that if we have Darwinism, if you have this objectivity emerging out of your dynamics, then you can describe the information from the central system that leaks to the environment by a non-contextual ontological model. So if you take this as your definition of classicality, in this approach to quantum Darwinism, you can say that this objective is classical. Very interesting work. And now the central topic of the seminar today, the application to this anomalous heat flow. As I told you, this is basically, this work started with Naim, which is a former student of Gabriel Landi, and Gabriel Landi was at the University of São Paulo. After he left, Naim and Luis, his former students, they started working in my group, and I learned a lot with them coming. It was really nice. And this problem of connecting contextuality and thermodynamics, it started with the work of Matteo Lostaglio of 2020, this PRL. And what we do is to extend what he did here in a way that it can be applied to many more models. I'll try to make it clear later. So the first thing in our paper, which is something that Matteo also does, and that is it's really interesting by itself without the application in thermodynamics, is to study specific scenarios where you have transformation equivalences, and we derive bounds for expectation of observables if those transformation equivalences are satisfied. And then we apply this to this specific problem in thermodynamics. But this itself can be applied to other applications as well. So the idea here is that the system is subjected to some transformation T. Here we are using this label T because we have the idea of time evolution, but it's not necessary. It could be steps. But the idea here is that you have a unitary evolution, and that's why this T is there. And I'm measuring some observable A, which is just measuring some M, measurement M, but to each outcome, I will attach a real number, positive real number. And then I take the mean value of this observable at time 0, and then I take the value of this observable at time t, and I want to see what is the difference. This definition here as the proper notion of how you see the change in operator A is also debatable, as you perhaps know more than me, because this is something that you cannot measure directly, so there are issues here. But again, I'm not going into this, especially here, I'm not much aware of the problems that arise. But this is also something that can be debatable. But for now, I'll be a bit practical. I'll assume that I'll have this and see what we can get. But also something that requires more work in the future. Okay, so the first result of our work is a generalization of the result of Matteo Lostaglio. And if this operation T satisfies this operational equivalence, in which this thing and this thing are some transformations, I don't know exactly which transformations they are, but they exist. And this is the identity transformation. So if this equivalent is satisfied, then any non-contextual ontological model predicts that the change in some observable has to satisfy these inequalities here, where this A max is the maximum eigenvalue in quantum theory, right, of the observable, but the maximum value that that observable can achieve. The proof of this thing here is a bit technical, but it's not that difficult. You kind of use this to find bounds on the stochastic map that represents this transformation, and then you get this, put these bounds into the equation for the probabilities, and you do some derive some other inequalities using the fact that these quantities are probabilities, are stochastic maps. So the proof itself is not difficult. The difficult thing is to have the idea of coming up with these operational equivalences. In the work of Matteo, the things that this alpha is equal to 1/2, and here we generalized it a bit. So this is not that interesting, but it's already something that goes forward. The really good part is this one, the one that is actually useful for us, is that when you have your transformation composition of these two, and these two satisfy these operational equivalences, then any non-contextual ontological model predicts that this should hold, where these quantities here, B minus and B plus, are given by these formulas here. The important thing here, this is a bit technical, but the important thing here is to notice that these inequalities here, that this mean value is bounded by these things that are linear that are not linear, but they are order 1 in P. This is the important thing to remember. It will appear later. And this was the nice idea of Naim that we developed together, because this can be applied to a much wider situations, so many more models than the one that we had before. And this came up because we started trying to apply these to specific models, and we couldn't find much parameters, much situations in which this could hold. So this is nice, but it was not much useful because very few models satisfy this. Then there was this, it's a bit uglier, but it's much more useful. Okay, now we go to the physical problem in which we want to apply these things. So as usual, we start with some Hamiltonian. We have interaction here. We will assume that we are in the limit of weak interactions. And the transformations I'm going to look at are just the unitary evolution of my system. In principle, I could apply this to any system. For the seminar, I will look at a 2-qubit model and make a few restrictions. First, conservation of total energy. So I demand that this happens. I'll assume that my state starts in the reduced states of the 2 qubits is a Gibbs state, and that we have Zeeman local Hamiltonians in resonance. So a lot of assumptions. I'm decreasing the kind of model I can apply to, but even in this restricted model, the first theorem was not useful. So we even in that situation, we still needed some more strong result. So this is a nice result. The second nice result of our paper is that in this situation with these restrictions, well, here the restriction in the states, the reduced states, does not come into play yet. Here I'm just talking about the transformations. But here we have that the unitary evolutions satisfy these constraints, which are exactly the transformation equivalences that I had before. And here is important. With this piece given by this sine squared of GT inside. So the bound on the, let me remember here, this bound is order 1 in P, as you remember, order 1 in P. And P is order 2 in GT. So this implies that this thing here is order 2 in GT.
And minus GT was interaction of the G.
Yeah, oh, my mistake. The G is the strength of the interaction. It will appear later. I should have put it before. Sorry. So for any non-contextual ontological model, or in my working definition of today, classical model, this thing here should be of the order of GT, of order 2 in GT. Okay? Now we look at the quantum prediction. Without these assumptions, I can compute these things explicitly. For the 2-qubit case, the density matrix will look like this. Also, I can give expressions for this piece here, but I'm not going to the details. And here the G appears. And I will highlight here the things that are important that will appear later. These of diagonal terms and the strength of the interaction G. And now we can compute explicitly the quantum prediction, and it gives us this term, which I did not show you, but these terms depend on these guys here, on the diagonal terms. And this other term that depends on the off-diagonal terms. So this.
So that was the energy of the system?
Yes, is the, I'm looking at the energy of system A in time 0 and time t. And I'm looking at the mean of the difference. Again, you have that problem that it's not something you can measure and everything, but given the definition of heat, you have this. And this term, the first term, is of order GT squared and is responsible for the standard heat flow in the absence of correlation. So if you just get some classical model, you get something similar to this. But this term has sign and magnitude that depends on the coherence and interaction parameters. And depending on the relation between these parameters, this thing can give you an inversion of the heat flow or increase in the heat the usual direction, but you have more heat than it would in the classical case. More important, this term is of order 1 in GT, which means that for very small times, you have to look at the parameters but to see this. But whenever this term is non-zero, there will be a difference between the non-contextual ontological model prediction and the quantum prediction. And this gives you a witness. So this figure we actually made with the parameters from this experiment here. It does not mean that we were looking exactly if these could be applied to the experiment, because our results, they're still not meant to be used with imperfections and this kind of thing. But we wanted to know if, at least at the parameter region that the actual experiments are being conducted, if we could see the phenomena happening. And it does. So we have now to change a little bit in order to be able to apply these in situations with imperfections, but it seems promising. So our main result, let me see if I can move this. Okay, is that with all these restrictions, 2 qubits, local equals Zeeman Hamiltonians, local Gibbs states interacting via an energy preserved unitary, anomalous heat flow is possible in some interval that depends on the point in which those curves cross, only if non-contextual models fail to explain the data. So what we have is that in this interval, anomalous heat flow cannot be explained by any classical model if you take this notion of classicality that we did here.
Okay, so what's the anomalous heat flow?
Huh?
What is
Is when the flow, the heat flows from the hot, from the cold to the hot system. It consumes correlations. We want to see if, what is the difference for this phenomena if you use classical or quantum correlations. So this, in this region, in this regime that we are studying, it only happens if you have genuine quantum correlations. Okay, there's a lot to be done. So what I told you today, let's just make a recall of what we done. I tried to introduce non-contextuality, generalized non-contextuality as defined by Speck and as a definition of classicality, mention some applications and, for example, state discrimination and Darwinism. And the main result that I wanted to talk about is heat flow inversion. And our main result is that we have this inversion in that regime only if you have genuine quantum correlations. And in the paper, I'm not sure if this version with the qubits is already on arXiv. I will check, but in the first version that was in arXiv, it was with qubits, but we were able to generalize it to qubits. But for qubits, we only look at the swap interaction. So it's not, we generalize the dimension, but we restrict even more the kind of map that we are considering. So it was mainly to say that it was not something that depended on dimension 2. And we see that it is possible to apply this to today's experiment. And one of the things that we have to do is to actually look at the experiments to see if these things can be seen there, the experiments that already exist. So next, what we want to do is to look at these theorems 1, 2, and 3. But here we just imagine that everything is perfect. Now we have to take imperfections into consideration. And we have to do everything again, all the calculations again, taking this into account. Other definitions of classicality, there are many. And one of them has already been investigated in this problem, which is negativity of quasi-probability distributions. And contextuality implies negativity, but negativity is not enough for contextuality. So they are related, but they're not equivalent, something that it would be good to check. And as I told you, our theorems 1 and 2, they're general. We apply these to this heat flow, but they could be applied to other applications as well. So this is something that might be interesting to check.